All right, so now let's wrap up what we've been doing. So with a generally high-level overview of the whole thing. So first, a word on the fact that in spite of learning all of that, data denormalization, trees, there are also graphs and cubes and other shapes, it is still true that for people in the industry starting a new project, tables are still here. And in fact, in 80% of the cases, tables is what you need. A relational system is what you need. In fact, many people have data that fits on a machine and they have data that is structured. In that case, just use a good old relational database. That's good enough. Then even if it's big data, you might still have a table, right? This is the whole point of data frames and HBase, Hive. You can actually still use tables. So do not underestimate the power of tables, right? The trees are useful for data that is not clean or in order to denormalize the data and so on. But in the end, it is still the case that a lot of data has actually a tabular shape. My computer on strike. Okay, no, it's just slow. You just use the keys. All right. Now you know the shapes, right? Trees are the shape that we studied the most in this course. Now we know that it's denormalized tables, right? A collection of tree is a more generic case of a table. A table, in fact, is a collection of tree that is flat and homogeneous. Who understands that now? Right? Okay. So, oh, and now it went all the way to the beginning. I don't know where it's acting up. Yeah. So, and then what we did not cover is graph databases that I do in the master's lecture in the big data. So Neo4j, for example, but it's the same. It has a query language and so on. Cubes are covered in information systems for engineers. And the text. And now text has multiple models. Now we even have vector databases. I thought of creating a sixth shape actually for vector databases, but then I realized this is just text. I mean, in the end, what we use vector databases for with the word embeddings or the documents is a way to model text data. One of the principles that I hope you saw throughout the semester is simplicity. The only way that you can scale to thousands of machines is to keep things simple. For example, you have a huge collection of trees, right? A huge collection, like billions, trillions of objects, and then each object is a tree. That's the simple thing. Like in S3, key value pairs, you have a key value model, you have object IDs and bucket IDs, and then a black box with the bits. That's also simple. Right. So it's very important to have something that we understand, because otherwise it's going to make our brains explode. So then what's very important is that each one of these data shapes, the 5 data shapes, they have a paradigm, so a story that you tell about them. They have a data model, maybe several data models sometimes. They have a syntax. They have query languages. They have architectures in the way that you implement the systems. And then you can even map them to each other. So the idea, for example, is that for tables, let me take the tables. Tables, you can select, project, rename, group, join, sort, union, right? That's the good old SQL with PostgreSQL. Cubes, you can slice, dice, aggregate, roll up, pivot, cross-tabulate. You might be familiar if you visited information systems for engineers. Otherwise, you're not, because that's not the material of this lecture, but just as a comparison. Trees, now you can look up, navigate, normalize, denormalize when we turn them into nested data. When we normalize it to flat data, we can validate, select, project, group by, also makes sense for trees. Graphs, we also did not cover them here, but we can traverse graphs, we can find patterns, select, sort, and so on. There's plenty of things we can do. And when we have text, we can filter, map, group, aggregate, and so on. But in fact, we can even find proximity, like similar words, similar documents, and so on now with vector databases. What about syntax? For tables, you know it's CSV, one of the popular syntaxes, even though a lot of people export their tables as a SQL script, actually, that you can re-import. That's a common practice. Trees, now you know, JSON, XML, BSON would be the binary version used in MongoDB, Parquet, if it's normalized, if there's a schema, Avro, protocol buffers by Google. And then there's also syntaxes for cubes. XBRL, for example, is the popular syntax for financial reports that are cubes. used throughout the world. Then we have RDF over XML, Turtle, and so on for graphs. Text, well, it's just text, right? So you just see it as it is. So again, you see that this idea of syntax is for every shape. Then query languages. You know SQL for tables. Now you know JSONic for trees, but there's others. XQuery is actually the cousin of JSONic that is on the XML side. We have AQL, Nickel, Uncle, Particle, GraphQL. I'll come back to that. For graphs, we have Sparkle, Cypher, GraphQL, and so on. But for graphs, it is converging. There is now a successful round of standardization going on. I think it's already there. It's an extension of SQL, and it's beautiful. So it means that now the industry for graphs is agreeing on a standard that they are now going to all implement. And for text, well, it's the query languages, right? That can be your own code, but you can also imagine a query engine. When you chat with ChatGPT, you just talk in English, right? So that you could also argue that for text, it's also natural language for the query. All right, so you remember the progress made, that we are now extremely faster with the quantity of data that we can store in data lakes, because now it's absolutely gigantic. And now I saw that there is even progress on DNA storage. Now that it's incredible how you can store, I think, petabytes of data on a credit card with DNA storage. Can you imagine petabytes in my hands? So this is also going to just become larger than that. But already today, if you compare to the 50s, we are more than billions of times, we have billions of times more capacity per unit of volume, right? I even looked at it per unit of volume. But the throughput, the speed at which we can read, has not increased that much. And the latency, it's even worse. It has only been reduced by an even smaller factor. And by now, hopefully, you see that all the things that we built in this course are because of this. We parallelize because of the capacity and throughput that didn't increase the same. So here the solution is to parallelize, right? And for the latency problem, the solution is to batch process. We have chunks, blocks of hundreds of megabytes, and we have the log-structured merge tree architecture in HBase that allow us to, when we write down to the system, we write down with huge quantity at a time. We don't write down bit by bit, but we write down 100 megabyte by 100 megabyte, right? So we saw, and again, that's because of this, that we scale out the collections of trees to multiple machines. Now we have data centers with thousands of machines, and we spread the trees all over the machine. This is what we call scale out. So scale out, scale in is the opposite. Scale up means you build more expensive machines, scale down, less expensive machines. Then we saw that we can go to heterogeneity and nestedness by switching to collections of trees, but this is on the individual record level, right? Every record now is a tree instead of being a flat record. Plus the records might have different columns. For the types, we saw that it's more or less universal. I mean, it's like a Schweizerdeutsch, so the exact names might vary, but in fact, the types are more or less the same everywhere, no matter what system you look at. Now you can take any new system that we have not covered. You can look at the documentation. You can be sure that more or less it's going to feel the same in terms of types, right? We have strings, we have various kinds of numbers, integers, decimals, doubles. We have binary data, dates, time, and we have structured data with typically objects and arrays. Sometimes objects can also be in the form of either maps or structs, which is a subtlety, but in general, it's really objects and arrays, the structured level, right? So you will very easily learn any new system like this, any new schema language, any new formats. That should be easy because again, it's the same paradigm. You just need to learn every time the new names, how it's called, and the new list. Then we saw the two directions. When you have data, you can serialize it, meaning you store it to the disk, right? You can serialize, for example, trees. What is it doing? You can serialize trees as XML, as JSON, as XQuery, and so as in all kinds of formats. Then you can use, you can validate it with XML schema, JSON schema, and so on. You can query it with XQuery, JSONic, store it as Parquet, Avro, and so on. So now you know all of these technologies. Yeah, that's pretty much what I want to say. So remember the names. Serialize means you take something in the memory, serialize, you store it as bits on disk. The opposite side is called parsing. You parse, you serialize. You parse, you serialize. These are the two words. Okay. Then something that we didn't really cover is the fact that we can, in fact, map shapes to each other. It means that we can store trees in tables. We can store tables in trees. Storing tables in trees actually is very natural because a table is just a flat tree, flat collection of trees. Trees are easy to store as graphs because the graphs have cycles, but the trees do not. So graphs are more generic than trees. A graph can be stored as a table. How? Because a graph is just a collection of nodes and edges, right? So you can just store it as a table with 3 columns with the source, the destination, and the property, and then you just store a graph as a table. A bunch of text can also be stored as a table, even as a vector database that would be tables with vectors in their columns and so on. Why do we do that? Because sometimes you have a specific system available or a specific license, or maybe you have a system that scales very well, but you do not find any system that supports the different shapes. So typically when people implement a first prototype, they will use an existing system and then implement a mapping like that. And typically a few years later, they are going to switch to a native system where they do everything themselves, but this of course is more work. So it means that the very early versions of graph databases or of document stores, in fact, were implemented on relational tables for this reason. And it's later that came the native versions for trees and for graphs. Okay. The same goes, by the way, for vector databases. Now there's vector extensions for relational databases, but now we are going to move on to native support for collections of vectors for large language models. Okay, so now the idea of an architecture, by now I hope I convinced you because of data independence, is that the way you store the data should be completely hidden. You shouldn't care what it looks like. That's hidden from the user. The user sees a data model and they think in a data model. They see tables, they see trees, they see graphs, you know. The execution layer should also be hidden, right? You might use a system that looks like MapReduce or Spark, but in the end, it is not desirable that the end users learn Spark or that they have to use Spark directly. Spark or MapReduce normally should be just for the engineers who implement the systems. The end user should have a fancy declarative language. SQL, JSONic, MDX is for cubes, Cypher for graphs, and so on and so on. This is how you make it more accessible to users. And I could even add on top, I'll come back to that, but natural language that in the end, with large language models, this might go in this direction, right? So this is the language landscape where you have the software engineering landscape with the assembly code and then Java, C, R, Python, and so on. That's the software engineering. With this distinction between the low-level languages and high-level languages. And the same goes for data. We have the low-level languages that I call proto-declarative. And here I have MapReduce, the MapReduce APIs, I have the Spark API in mind, and so on. So these are all the low-level languages. And then you have the high-level languages like SQL, like JSONic, and so on. And then this is out of scope of the lecture, but the same goes for machine learning, right? Now you have machine learning libraries, TensorFlow, PyTorch, and so on. But again, these are APIs. You use Python with an API to do machine learning. This, in fact, is very similar to the Spark or the MapReduce API. And in the same way that in Spark or in any system, you can have a higher level query language, the same is going on for machine learning. There are people designing higher level languages for machine learning. Instead of having to use PyTorch or TensorFlow and having to code in an API, people are designing higher level languages with which you directly declare that you want to train that data set on this and that in this and that way, right? Okay, so that's the landscape. So that's now, by now, you know RumbleDB. It will also be in the exam, you'll have an installation of that. It is relatively stable, so that's actually a stable release. And that will be the one we use for the exam. So now you know that there's the Docker. You can use the Docker to use it. On exam day, it's not going to be Docker. It's just going to be installed on the machine, right? But it will just work. So you don't have on exam day to worry about that. What we saw too is the idea of sharding and replicating the data, right? Many systems at large scales do this. So sharding is the idea of having blocks, right? We have blocks in HDFS. We have splits in MapReduce. We have partitions for RDDs in Spark and so on. So we shard the data, and that's how we spread it over machines. And then we have the replication of the data. It means that every one of these shards, or chunk, or block, or splits, or partition, or whatever we call it, every one of these shards is replicated. Typically, we like to do it 3 times. It keeps moving the slides. Typically, 3 is a good number. By default, we tend to store everything 3 times, but you can also change it. If you really want to be sure, you can have it 4 times, 5 times, and so on. That's the importance of doing backups. And in fact, there was a recent piece of news that taught us that it's also important to do backups across cloud providers, right? To not just be only on AWS or only on Google Cloud or only on Azure, but be on several providers and make sure you have at least a backup of your data in a different cloud provider, just in case you lose it on the first one. It actually saved a company recently that they had a backup, because otherwise that could have been a huge mess with hundreds of billions of dollars. So this is a good point. And then the companies that have maybe more customers or that are even more bigger, they don't only have backups, they in fact really use the 3 clouds at the same time, right? Typically, if you look at Netflix or Apple and so on, in fact, they use multiple providers, not just for the backup, but really for production. Like whenever you connect, it might be to Google, might be to AWS, might be to Azure, they just use all of them. So even if one of them fails, it's going to work with another one. Okay, so replication. It's really going crazy today. All right, so then we have batch process. Batch process is this idea that we like to group the data we want to process in batches, in chunks, right? So that's what we did with HBase, where we needed to write new data to HDFS, but instead of writing the data every time something happens, we accumulate the data in memory, and only when the memory is full, we store the data, because it needs to be sorted. That's the reason. And then we merge and merge and merge. Remember, we flush, we compact, we flush, we compact, and so on. All right, so now with everything you've learned, you should be able to learn new products. They more or less work the same. So if you know Spark, you know equivalent products. You will learn new schemas, formats, and so on. Should be easy. You should be in a position to choose which product to use now, because you can look at the characteristics, and in particular, what's the shape of your data, what's the quantity of data that you need to store, and so on. So do you need PostgreSQL? Do you need a data lake, and so on? And maybe for some of you, even more so for computer scientists, design a whole new technology, because then you might realize that it's not enough and nothing on the market does what you're looking for. In that case, you could design a new product. But at least if you know what exists, you will realize when you do not need to design a new product, because you can just reuse existing products. All right. So again, to make these decisions, you need to look at the shape of your data. You need to look at the size of your data. Does it fit on your laptop? Does it not fit on your laptop? I really have seen a lot of startups in young age, in their early days. I saw a lot of success in some startups that managed to squeeze all their data in a single machine, because then they didn't even need to bother with the cloud and clusters and Spark and so on. You wouldn't imagine all the money you can save when you manage to make it work on a single machine. This is really something that is very important to consider, if that actually can be done with a single computer before bothering to go to the clouds. Then you need to consider what you want to do with your data. That determines the indices that you're going to build, and so on. And you really need to ask yourself, are you reinventing the wheel? Very often, people write code in Python, in Java, and so on, but actually they are writing code that was already written by a million other people. And this is just a waste of resources to see that done all over and over and over and over and over again, because very often things already exist, things already have been designed, people already made mistakes and learned from them. And in many cases, you can really just use existing technologies, existing languages before you need to invent new ones. So always, whenever you feel like you invent something new, first check if it doesn't already exist, right? A bit of critical thinking in there, right? And here I insist on the using one laptop, right? Normally you should only start using a second computer or even a cluster of machines once you know how to use the first one, right? You would really be surprised what you can do with these laptops. Just these small laptops here, it's incredible with all the cores now. There are 16 cores, nowadays 8 or 16 cores. You can do really, really, really a lot, even on a single laptop. Right, so that's a reminder of my definition, right? Big data is we are solving the problem that there's the discrepancy between capacity, throughput, and latency. And because of that problem, we needed to invent completely new technologies like data lakes, HDFS, MapReduce, Spark, and so on and so on. So what's in for the future? So I have a few thoughts. Some of them actually went kind of realized or are making progress in the meantime. I really think, and I'm repeating myself, that Spark, MapReduce, and so on, they are really not meant for the end user. Now, there's a lot of excitement also on social media, how cool it is to use Pandas and Python and so on. But really, the end user in the end shouldn't have to deal with that. There should be a higher level query language that they can use. That's the spirit of data independence. And this is what happened with SQL and relational databases. So that should be in the end invisible. Hopefully, people will realize that the data shapes are important. Why? Because that's determining how much resources and how much money you put in it, right? It's about productivity, it's about performance. It has a huge impact on how fast your system will be if you select the right data shape. And maybe new shapes are going to be discovered. In fact, vector databases are kind of a new shape of data, right? I didn't yet add it as a sixth one. I still keep it under text, but maybe one day I'll just split it and make it a shape of its own, right? So it means that this is not forever we're going to have these shapes, but there will be new shapes that might emerge over time. But remember that for every shape, it's the same story. You'll have a syntax, you'll have a data model, you'll have a language, you'll have an implementation. The first implementations will be on top of other shapes. Then at some point, you'll have a native implementation of its own. That is something that we can learn from history, right? Even if we have new data shapes. Querying should hopefully get standardized. I mean, it's already the case for tables with SQL. It's already the case for graphs now, as querying graph is also being standardized. There is a bit more work to be done with trees, because in trees, I think this situation is best summarized with this XKCD. Who likes XKCD? It's a popular comics on the internet. All right, so this is one of my favorites, right? And this is exactly what's going on with languages for trees. Situations, there's 14 competing standards. I even keep a list of them, so this is just a few of them, but I think now it's even by 30 plus. And then once in a while, at some company, engineers realize that we need a language for trees, and so they invent a new language for trees. Or they want to unify the language for the languages that already exist because they think they know better. And then what happens is that there's a fancy new website that introduces the new language. If they have a lot of money, they might even get adoption and so on. And then you basically land in this situation that you just have one more language. And it keeps increasing and increasing and increasing and increasing. And the list keeps growing, right? And it's a shame because technically XQuery is already 20 years old. It was designed for XML. it was already standardized because there were people from IBM, from Oracle, from Microsoft, I mean, from plenty of companies that worked for years to standardize that. It's already standardized. JSONic is just xQuery for JSON, but it's again following the same standard. So what's a bit sad is that many of these languages do not have a specifications. They are put online. There might be an implementation. There might be a few examples, but people underestimate the years of work and the number of people you need in order to have a precise specification that handles all the corner cases, that throws all the errors and so on. It's basically the design of a language costs millions of dollars. So before companies invent new languages, they should really consider if there's not an existing standard that can be taken over, right? But the features are similar. I mean, I taught you JSONic, and you will see, you can take any of the other languages, you will find the similar features. So you can learn any of these languages very easily with what you have. Then it goes in the direction with ChatGPT that we talk to databases, and now it's becoming clearer and clearer every year. I mean, a few years ago, I was just showing this Star Trek, The Voyage Home, when Mr. Scott was just talking to the computer. Now I think nobody would even laugh anymore because it's just normal. I mean, this is becoming a normal thing to do, and that's probably going to develop. Don't forget that we need to overestimate the speed at which this develops in the short term. So it might be slower than we actually think in the coming year, but in the coming 10 years and 20 years, typically it's faster than we think. So here we tend to underestimate the changes. Data might become fungible. That has to do also a little bit with the efforts to store some of the data on distributed ledgers, like blockchains and so on. When you consider collections of like graphs, for example, it's just a collection of nodes and edges, right? So you can easily shard them and share them and so on. So this is the notion of fungibility of the data in the way that it's flowing around. This is directly related to the notion of cryptocurrencies, which in the end, I'm not saying any cryptocurrency in particular is a good investment or anything. That's absolutely not what I'm saying. But I'm saying that the principle of that is just to realize that the notion of private property or the notion of owning money or of owning something, in the end, is a matter of agreeing between humans who has what. And when you agree on who has what, it comes down to just keeping track of who has what. And so this, in the end, ends up being data, right? So this is why there is some sort of convergence here. Of course, that comes with risks, and this is why now there's important topics like data protections and legal aspects, which are very, very important. And now it's also something that more and more companies become aware of and are even forced to do by law in the EU and in Switzerland. So just because you can do all of that doesn't mean that you shouldn't be careful with doing all of that. And you need to remember that that the data might be sensitive or that it might belong to other people. Then we have some interesting interaction between machine learning and databases, and there's this ongoing joke that we don't know if machine learning will eat databases or databases will eat machine learning. But some of the interesting developments in this direction is that, for example, people are building indices based on machine learning. Instead of hashed indices, instead of B3, B+3 indices, people just learn indices. Like the index is a machine learning model that tells you where the data is because it's learned it. So this is very impressive, the sort of things that are going on now. So this is an example here of learned index instead of a hash or B+3. So it's interesting to see the evolution. This is done at MIT currently. Quantum computing is also on the rise. I realize maybe, I'm almost done actually, but maybe we should take a break because it's 9. I'm almost done, then I will talk about the exam and we'll move over to the quiz, right? Let me leave quantum for right after the break. All right, so I'll see you in 15 minutes at 9:15.